So 1 is a compound, or sorry, 1A compound. Check yourself, please. Different color pens. Sorry, you're starting to realize I have a method or a procedure or a routine. If you need a different colored pen, I can throw one at you. I'm hoping they all work. If a partner next door to you has one, that will be even more helpful. Corbin? Oh, sorry, that's a really awful throw. Okay, so you guys get some weird ones. All right, so 1A, pure compounds for pure substance. B is a mixture, sugar, water is homogeneous. C, mixture, homogeneous, plus soda is kind of bubbly, but it should be very, very uniform throughout. D is iron, Fe, iron, pure substance, meaning it's an element. E, steel, is not an element. It's not on the periodic table. So it's a mixture, but it's actually a mixture of two things. Does anybody know what steel is made of? Iron and carbon. Very good, which is going to help you. That was like part number 4 was an alloy. F, carbon dioxide is a pure substance compound because it's made of 2 elements. G, chlorine, pure substance, which is an elemental periodic table. H, steam is actually water. Water, H2O, is a pure substance because it's made of 2 elements, and so therefore it's a compound. I, homogenized milk, just means that it's milk that's been made so it doesn't have any curds in it. So it's a mixture. It should be homogenized, meaning it should be homogeneous or uniform throughout, because you don't see chunks in the milk, hopefully. Looks kind of nasty. I wouldn't drink that. Water, H2O, would be a pure substance because it's just 2 elements. K, salad, heterogeneous mixture, because you can definitely see the distinct differences in that mixture. Now, you could have put homogeneous if you were thinking of a different type of salad, maybe just all lettuce. I would say that's pretty homogeneous. That's why some of those are going to be a little flexible. L, calcium, which is a pure element because it's straight off the periodic table. Questions on 1? All right, let me just put 2 up here. You guys look at that first. Those are your properties. The only one where you could have potentially put a different answer was probably which one up here. Color change, because that's the kind of wonky one that you're not sure. Most of our color changes we'll assume is like dyes or things being a predictable color change, painting something, coloring something. That would be our physical property, unless it was a reaction. Over here on 3, those are your changes, and you guys did great on your homework on that one. I'll look back at some other friends who had put like lowercase c's. But you guys are doing a great job in identifying your chemical changes, so I'm not too worried there. F, milk souring. Sour kind of sounds like a property, like it tastes sour, but souring is actually a process, it's a reaction, where milk's reacting with some sort of acetic acid or lactic acid, something that's in bacteria, so therefore it's causing a process of souring. That's reaction. All right, look at 4. I gave 2 examples. So alloy is a mixture, and you can have 2 elements that are metals being blended together. You can have 2 elements being mixed together where at least one is a metal. There's so many alloys in the world. So did anybody recognize brass as an alloy? Okay, brass is not on the periodic table. It's actually copper and zinc. We will make brass in about a month in the lab. It's kind of cool. And then we already talked about steel. Turn, tell your partner next door which alloy you chose. If you didn't choose it, all right, and come back to me. We are going to watch 2 quick videos, okay? So, in terms of what I'm looking for, whenever we watch a video, a lot of times we can watch and we can learn, we can pick up pieces, but I want you to just do a couple of bullet points of things that you find out. It can be interesting facts, it can be chemistry related, it can be something you're like, oh, now that makes sense, like aha moments. So there's 2 videos, so I want a couple of bullet points, just a few, not like 15, but not 1. Okay, so get a couple down. And I'll take attendance. gonna turn off Pandora real fast. Okay. Oh, I guess I have to wait. And I'm gonna do the same, okay?
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of. The atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass.
That's your
This
title.
law says, take an isolated system defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see, they've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas.
All right, so I just picked up 2 kind of important pieces. See if you can tell if somebody next to you is one of those. I mean, try not to look at what I'm writing, okay? Think out loud for a second. All right, I hear matter cannot be created nor destroyed, and then simply it can be what, Corbin?
It can be like reshaped.
Well, I like the first one. Instead of reshape, use something else. Use the thing they're called. It can be changed, it can be rearranged. So they basically made new bonds. So matter cannot be created nor destroyed, but it can be rearranged.
They have a mind of their own. Let's see, they've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, nuclear reactions fused light elements such as hydrogen and helium to form heavier elements such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law because they release an astounding amount of energy seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later, got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.
All right, so pretty cool concept, but relatively simple if you can kind of just stay kind of organized and don't get too involved with the big thing. So we want to think about this matter and its relationship to energy, and then where the matter comes from in all of our chemical reactions. So theoretically, where did all the matter come from in our chemical reactions? Right, the Big Bang, right? So there's that theory, the Big Bang theory. It's literally called a theory. What the heck is a theory? Anybody?
It's like,
Well, we don't always actually, we actually never really prove things in science. We heavily support them. So we can do thousands and millions of experiments to continue to suggest a theory. I don't like the word prove because everyone's like, well, if you can't prove it, is it right? No, I mean, there's nothing that's certain out there. We have to assume that we are right because there's so much evidence, there's so much data to support it. But you're right, a theory is something that's heavily supported with lots and lots and lots of experimental data. Really unbiased data, things that are just scientifically supported, okay? So back to theory, we sometimes mix up theories and laws. So maybe tell the person next to you what you think the difference between a theory and a law is. Some of you guys are not taking advantage of your talk time. You have 30 seconds more. Try to name off 2 theories and 2 laws you know of. 2 theories and 2 laws. All right, come back to me. 3, 2, 1. All right, Riley, give me a theory you can think of. A theory you can think of. Big Bang Theory, okay. Give me something else, Estes.
theory of evolution.
Theory of evolution by natural selection, right? So we talk about chromosomes, some traits which are more advantageous than others. Maverick, in that theory? Okay, I heard somebody else say something. Theory of...
Dark matter.
Say again?
Dark matter.
Dark matter, okay. Relativity. So a lot of theories are super, super elaborate. So theory of evolution, which we're all familiar with because we just took biology, is you have an advantageous trait, somebody else mates with you, you make more of your offspring with that advantageous trait, and then population changes over time, blah, 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 blah. You can go on and on, right? It's a very, very long-winded explanation for data that is seen, or natural observations that are seen. Now some laws. Over here. Give me a law. Law of what? Motion. Okay, stop moves until you make it stop. I mean, until it moves in a different direction. Give me a law here. Conservation, mass, cheap. Okay, give me something else. What? What? Law of gravity. Okay, give me one more.
Newton's laws.
Say again?
Newton's laws.
All of Newton's laws which are not related to motion, all right? So, law of gravity. Say it as short as you can. No, don't even make it that elaborate. Stuff falls. Got it. Okay, so laws are very, very concise. They're not explaining anything. They're stating a natural phenomenon. Stuff falls at 8.3 or I might be right. 8.91 meters per second squared. Certain acceleration. So the law of conservation of matter, the law of conservation of mass, which are used interchangeably because matter has mass, is that matter is not created nor destroyed. That is as simple as I can make it. It is a statement of a natural phenomena, but there's no explanation. It's just simply, we like to elaborate and say, oh, it's rearranged. So you have that here, and you have that here. Are you good? Yes or no? Yes. You have to respond. Okay. So the way that we constantly talk about this is that matter is rearranged through chemical reactions, through chemical reactions, through chemical reactions. So we will talk about chemical reactions a lot, but I mentioned that here, like combustion, they mentioned 2 examples of combustion, methane and propane. Those are chemical reactions where the gas is reacting with what? It's like methane gas, cow farts. They held it up to a match, but what was it reacting with? Oxygen. And then those 2 things, methane and the oxygen, they reacted to make what and what? H2O and carbon dioxide, right? So we see the carbon, we see the carbon, we see the oxygen, we see the oxygen in 2 places here, we see the hydrogen, we see the hydrogen. What happened to the atoms? They just rearranged and they rebonded with new compound, or to make new compounds. And in that rearrangement, there was a change in energy. So like some energy went into this process because we lit a match, but then a bunch of energy comes out of this process because that's what combustion does. It releases lots of fire and energy. So we can talk about energy being conserved as well, but that's going to be more related to something down the road for us. Okay. So as you can see, reactants are on the left side, products are on the right side. So if you don't know that, now you should know that. Okay. So this is an equation you're familiar with, right? Did anybody do the photosynthesis dance? Oh, okay, so just do it in your seat, okay? So the sun, do it here, okay? The sun, the rain, aka don't get crazy. It's water. Okay, the sun and the rain and the CO2 makes food, which is what? Glucose, food, and oxygen for me and you. Okay, that rhymes, right? Okay, so the sun and the rain and CO2. Okay, so you know the chemical reaction for photosynthesis. We know it's carbon dioxide that plants take in from us breathing that out. They take in water. Little sun helps the energy, puts the energy in to break these bonds, and then they poop out glucose, which they can use as starch in their building of cellulose, and oxygen comes out as a waste product. But we really like that waste product because we could not live without it. How many carbons total are in the reactants? You have 30 seconds. Talk to your neighbor. My bad, there are 6. I was looking at oxygen, my bad. I'm sorry to confuse you. There are 6. Now, what is this little tiny number behind the O called? Subscript, right? So a subscript is sub. What's sub referred to, like that prefix? Below, like a submarine goes below water, so it's the number below. If there were a number like this up here, what would that be called? Not an exponent. Superscript. So super means above, okay? Like Superman, okay? No, but super means above. Or superficial means like you care about like the, outside observation. All right, so 6 carbons. How many total oxygens over here? 18. So this 2 and the coefficient of 6 get multiplied to give us a total of 12. And this 6 times the imaginary 1 on the outside of the O gives us what? 6. So that's a total of 18 O's. So that's 6 carbons. Okay. How many hydrogens total here? 12, because that's 6 times 2. Okay, so that's 12 hydrogens. All right, discuss with the person next to you how many carbons, hydrogens, and oxygens are on the product side. All right, how many carbons? 6, just from that right there. Okay. How many oxygens?
18.
So 6 plus 6 times 2 is 12. 12 plus 6 is 18. And hydrogens, 12. Okay. So was matter conserved? Yes. And we have to make sure we don't break the law. The law is law of conservation of matter. We make sure we don't break the law by adding coefficients. So essentially, the reaction, carbon dioxide plus water makes glucose and oxygen is just the photosynthesis reaction. But we make sure we didn't break the law by us artificially putting in a 6, and this last one over here, so that you have a total of 6, 18, and 12 atoms on that side, and 6, 18, 12 atoms on this side. So we overall use the coefficients to help us not break the law, to follow the law of conservation of matter. Okay? So we'll talk about balanced chemical equations a lot more, but that's just one example. All right, so we're basically going with notes. Okay, pull out a piece of paper, call it Law of Conservation of Matter Lab. We don't need that. We already kind of did that one. We will balance more of these at the end as we get you guys started in the lab, okay? All right, so just stick around for me first. I need to see your material. Using your bottle? Yes. HCO3 sodium bicarbonate fancy baking soda. Acetic acid, fancy chloride. Vinegar, we have to do a baking soda and vinegar. We have balloons. We have this like little waxy paper, it's called wave paper. Normally what we base substances in. On the scale, but I would never put chemicals directly on the scale, ever. I usually weigh them in something like this.
A wave?
A weigh boat, right? So I didn't give you weight boats today just because they're bigger and more cumbersome. I gave you weight paper because it's lightweight and you can actually manipulate it a lot better. Lastly, this is a pipette vinegar out. Some of you guys realized this last time, but on the pipettes, you see, some of you guys saw there were like little milliliter markings. You can either use the milliliter marking if it's a very like small amount of volume you need, or you can use the what to measure. Graduate 100. Do you need to measure anything? No. Okay. So that's those are your materials. The lab is in. Okay. So the lab is in the lab notebook, but I do want to make sure you know what's going on here. So at the end, you'll make sure that you wash out the soda bottle so there's no trash left over in there. All the chemicals will be neutralized because sodium bicarbonate, baking soda acts as a base. Vinegar, which is acetic acid, acts as a acid. Acids and bases neutralize each other, so everything's safe to go down the drain. At the end, you have to run percent error. So percent error is going to be based on what you thought you should have gotten in the lab regarding conservation of mass, which you'll talk about in your groups in a second, to what you actually got in the lab. So I'll leave this here and you guys can interpret what that means as you get there. And then at the end of class, we're going to try to knock out problem set 1. Okay? Okay, so your labs, though, have changed because some of you guys are getting to the point where you're either not working well together or too comfy. Where are we at? Okay. So do look at the lab group name or groupings and then go to your lab, okay? Go to like the lab number you were at. Hannah. Find the lab called Law of Conservation of Mass or Matter. Okay, so let's see homework. Because I'm usually coming out with the not Alright, you guys need goggles on. You know that's obvious. Send one person, not all 30 of you. One person gets goggles for you. Thanks, dear. Here, I got you. So the law of conservation matter really the one with the balloon on it, so make sure I have like 2 balloons on the side. Make sure it's the one with the balloon. It looks like this, it's probably sideways. Probably sideways.
I can't read today.
No, no, you're fine. Okay, yes. Where's your I gotta go pass. Yeah, so I can sign it and give it to you. The pass to go.
Yours.
Thank you.